Okay, hi everyone, and thanks for inviting me to this fantastic workshop. And Florence, of course, is beautiful, and GGI is great, and I'm happy to be here. I'm going to talk about this idea of late universe phase transitions, and this is work done together with Salvatore Bottaro, who's here, Diego Redigolo, who is somewhere outside, and my students Maya Tsur and Ben Hatzofer. Oh, here's one of the culprits. So, so the idea would be very simply that so let me just say it like this. Phase transitions have been the topic of insane amount of studies in the past decade. But this, I think, is a huge hole that has not been covered. And this is what happens if there's a phase transition after the CMB. You can also consider the case of the CMB, where the phase transition happens at recombination. This is also very interesting. But I think what we are focusing right now is what happens if it is after the CMB. And so let me just start with the following, right? So the whole idea here would be that we have the regular lambda CDM, we have the regular perturbations that originate at with some primordial spectrum, probably from inflation, okay? And what we're going to assume is that there is a dark sector, okay, where the main part to remember is that the dark sector, the dark sector abundance, the total density of the dark sector, never dominates, is always subdominant, such that the homogeneous, the background evolution does not change. Okay, so basically that we have new row of dark sector of X, where the row of dark sector of X is always less than, say, 10 to the minus 2 of row total at any time. So never in the history of the universe, the background evolution was affected by this. Okay, so yeah, sorry. I mean, it's a dark sector for now. It could be the sector where dark matter resides, but then the new stuff apart from dark matter would be this. The total row total at any time. So if you ask me about what about ineffective constraints, they're gone. They're not there. What about any constraints on the evolution of the universe? Nothing, okay? But the whole point is that the regular lambda CDM, the standard, our standard understanding of the universe is that the universe is extremely homogeneous. And so if you add inhomogeneous sources, you can see them even though their density is very large, very small, sorry. So that is going to be the main idea. So the idea is that the row is less than row total by a lot, sometimes 10 to the minus 5 even. But the whole point is that the delta row can be as big as 10 to the minus 5 of the row total. And we know that this is roughly the size of the delta row in lambda CDM. Okay, this is the main idea. Okay, sorry, yes. Let me find maybe a broken chalk. I mean, I think this just means you have to buy better chalk, no? Right. And so as you see, the main idea is that as long as delta rho dark over, well, let me call this delta rho dark over rho dark is big, okay, is significant, we can have this effect being observable, okay? And so we do not worry again about background evolution. I'm always asked this when I talk about this idea. Background evolution is not changed, okay? You're not sensitive to it, apart from very, let's say, edge cases where the phase transition happens very late, okay? And let me also say, and importantly, there was a paper today on the archive of my collaborator Yushin and Seth and one more student, I think, that I don't remember his name, so you can check it, which dealt exactly with that case, where the phase transition was happening. Also, very similar case, but the phase transition was happening already at CC domination. Okay. Yes. Yeah, exactly. The contrast will be large. Yeah, exactly. That's what I'm saying. And as we will see, phase transition naturally give you this type of scenario, but not only phase transition. So I will mention one more sort of phase transition story, but not precisely, which exactly fits into this mold as well. More questions? Sorry. Okay. So in practice, as I said, we will think of this as less than 10 to minus 2, but delta rho around 10 to the minus 5 or below, and so we can observe it. And as we'll see, the observable effects will be both in large-scale structure and in the CMB. Okay, so this is what we are considering. Okay, so let me talk about sources. Okay, so the first source that I'm going to spend most of the talk on is first-order phase transitions. Okay, because the universe is homogeneous at 10 to minus 5 level, right? So 10 to minus 5 is the regular inhomogeneities that we observe. And so this is roughly where the experimental sensitivity is, right? So this is what you will be able to constrain if you want. Okay, our main constraint will be that this must be not larger than the errors in the current measurement of the power spectra, okay? And that's roughly at this level, 10 to minus 6 to 10 to minus 5 level, okay? Okay, good. So another source that I'm going to discuss very briefly is something that was discussed a lot actually in this conference, which is axion instabilities. And this is the case where there's a axion gauge coupling that I will very briefly discuss, but it was already discussed in this workshop. But also there could be other things that I'm not going to talk about today. So, but could as well be very important, which is topological defects. So things like cosmic strings, domain walls, etc. Okay, and so again, these could be also something that would have very similar effects, and I think they fall into these kind of dynamics. Okay, so can I move this? Perfect. Good. So let me start with the assumptions that I'm gonna be following throughout this talk. Okay, so and this will basically be a spoiler for most of the talk. So we're going to be mostly thinking about matter domination. Okay, and for most of the talk, we will assume that these perturbations that we produce here, this delta rho dark, will be produced very quickly, and I will explain why. Okay, and that we usually can neglect the dark sector after the phase transition, and I will explain also why. Okay, and very importantly, that all the effects are gravitational. Okay, so only interacting gravitationally. Okay, so this, to me, this means that that this scenario is very broad. Whatever you have that it's inhomogeneous, don't assume it interacts in any way with the standard model, and still you can constrain it, even if it's a very subdominant fraction of the universe. Yeah. On small scales, right. That's true, right, that's true. Good, so baked in here is the assumption that I'm never talking about things far from the horizon. Okay, so it's always pretty close to the horizon, right? If the phase transition, for instance, if the phase transition is very fast, and I will define what it means very soon, then you produce a lot of bubbles, and then the typical scale is deeply within the horizon. Then you lose sensitivity on one hand, but also you're probing much shorter scales. So then the scaling is a bit different, as you say. So right, typically, I'm imagining things within the horizon scale, or with only, and I should say in the phase transition story, for typical models of phase transitions, you're only the scaling between the size of the bubbles and the horizon only logarithmically depends on the parameters of the theory. Okay, this is this beta parameter that is I'm going to describe. Okay, good. And let me say what the constraints are. Okay, and then go into the model. So the constraints would be the following. So basically anything that is sensitive to such a scenario, but the first constraints that we thought about and that we analyzed here is from the CMB, right? So this is the phase transition is produced after the CMB. So this is the fact that there's lensing and ISW, and we mainly are describing ISW. Okay, so integrated Sachs-Wolf. I will explain how precisely. And then in large-scale structure, here we're talking just about the matter power spectrum. All right, but of course in the future, it will be interesting to consider the effects of tensor and vector modes, as I will explain in a second, and also non-Gaussianities. Sorry. So the reason for the fact that you get tensor and vector modes and non-Gaussianities is that these perturbations are not the primordial perturbations, where the slow roll of inflation was ensuring that the perturbations are adiabatic and that they are scalar, the tensor modes are highly suppressed, and that the non-Gaussianities are also suppressed. But for something like this that you produce, the only thing that's suppressing these things is just the effect that as I said, of the size of the bubbles compared to the size of the horizon, and that is only a logarithmic factor. So you expect significant non-Gaussianities, significant tensor and vector modes. And I think I didn't mention, but I should say that this is all preliminary. We still haven't published the paper. We're still deep within the calculations, and I'm going to describe also, hopefully, I'll get to some problems we are having with understanding, but we'll get there. Okay, so good. So this is after the CMB. So I don't see why you would produce distortions, but of course, if you produce it, sorry.
So between BBN and there was two different groups. Like there was Pedro Scholl and there was also
Yushin and Shubik and Gili Elor, yeah.
But if you have it after the CMB,
exactly. The photons are already emitted, so you don't distort. You don't distort them, right? Good. So, okay. So let me continue. Okay. So let me briefly talk about the other idea, because I will just mention this. This is a paper from several years ago already. Okay, so let me talk about model examples for this. Okay, so the first model is I'm going to talk about is actually the second thing, which is tachyonic instability, tachyonic axion instability. Okay, and this is a paper with, so this is my paper, and together with Sida Liu, who was my postdoc, and Yushin Tsai. Okay, so this was an example of such a scenario that produces something like this. Okay, so here, this was a scenario with an axion. A was an axion, and there's a dark photon. Okay, and the axion is not a dark matter. It's not the dark matter candidate. It's just an axion that's living there, misaligned from the early universe, but with a very small mass. Okay, so the mass is 10 to the, sorry, MA is 10 to the minus 27 to 10 to the minus 30 eV. So very, very light. It cannot be the dark matter. But it's until some point, it's just a CC. And then it starts when Hubble is equal to this mass, which is between today and recombination. Then you get that it starts rolling. Okay, and when it starts rolling, it has a coupling. You can ask me more about this if you want, but I'm not going to go into the details. It has this kind of coupling. Okay, and this kind of coupling produces a tachyonic mass for certain K modes, specific K modes that are of order up to alpha A prime over F, where this is the derivative with conformal time. And these modes are explosively produced exponentially produced until you start to saturate the point where you add friction to the axion stops. And these modes are very inhomogeneous. These are very long wavelength modes. Again, only logarithmically smaller than the horizon scale. Okay, and what happens is that this kind of thing produces these delta rhos for the dark photon and the back reaction on the axion. And in this paper, we were specifically looking at B modes, which could be, you can produce observable B modes, but also we put constraints from the ISW effect. I'm not going to go into it because it's very similar type of physics, but if you're interested, go to this paper. Okay. You can get visible B modes in like future experiments with like Lightbird experiments. So yes. So with the current constraints, basically put this constraint that the delta rho is about 10 to the minus 5, but you can have pretty significant B modes because again you produce all the modes similarly. So then yeah, we found scenarios where B modes were visible. So this was, so this is not phase transition. This is like a tachyonic instability, but this is after CMB, yeah. You do from reionization. So it's a small effect, but it's still significant. Yeah, good. So it's true. You don't get the B modes from recombination, but you get a small effect from reionization, and that effect is enough to produce some B modes. So that's exactly what we calculated. Very good. Okay, good. So let me move to the main part, which is the phase transition story. So first order phase transitions. All right. Exactly, good. So that was also one part of the, exactly. That was also one of our conclusions, that it's very different from the primordial spectrum, where you don't see the recombination peak and you only see the reionization peak. Exactly. I mean, it's not a peak, but it's like a broad, but you only see very low L modes, essentially. You don't see anything in the high L. And in fact, I think one of the limiting things of this scenario, why we were we're not pushing this forward more, is that all the constraints were from the low L region of all the spectra. So even if you see something, it's very hard to know that you do see something, and especially in the scalar part, because I mean, of course there everything is dominated by cosmic variance. Good. So let me talk about first order phase transition. I'm always asked, but what kind of phase transitions can happen that late? And is it possible at all? And the answer is that there's no motivation for this. Okay, there's no known source of a phase transition that we know happens at this range. But that's also true for a lot of other physics. Okay, but let me say it like this: that it captures a lot of very sensible and reasonable possibilities for what a dark sector could be, and I'll briefly describe one of these. Okay, and there's unlike even this scenario where you would need to require a very light scalar, which could be problematic with other things, this scenario is, I think, one of the most sensible ones in terms of new physics, and let me explain why. Okay, so I think I explained by example. Okay, so one of the well-known things in particle physics, right, is that asymptotic freedom. Is that if you have a gauge theory that's confining, the confining scale is exponentially dependent on the coupling at the cutoff. Okay, so in principle, if you have some SUN, okay, some dark SUN gauge theory, okay, we know that it confines at some point. That confinement scale can be anything. That's the whole point of dimensional transmutation. Okay, and what I'm going to be interested in is what if this dark SUN with a very small lambda. So if lambda is above EV, then we will have phase transitions before combinations. If lambda is between milli EV to EV, which is a very so this is lambda. Okay, if lambda, well, let me call it lambda SUN. So the lambda QCD of this theory, if this lambda QCD is between milli EV to EV, then this would be a model that we're interested in. Yeah. Right, good. So good. So I was going to plot this Columbia plot. Very good. So it's so I mean. Exactly. Good. Good. So beta would be 100 to 1,000, right? You group around. So that's fine. I mean that's exact. So 100 is still observable. Okay. So the point is that this is very sensitive. Okay. Unlike gravitational waves. So usually phase transitions are proposed for gravitational waves. Gravitational waves, you're looking into a very future thing that might not be even built if it's, I mean, or hopefully gets built, such as LISA, but then you're highly suppressed by the alpha and the beta, and you're looking at already at the future. Here we're talking about current data that is highly sensitive. Okay, so that's, I think, the big difference. We will show you the plot for different values of beta. Right, right. So 10 to the minus 2 is the suppression from the small density, let's say. Okay, so 10 to the minus 2, and then beta is 100. So you're roughly at the edge of sensitivity. So with current data. Okay, I'll show you the plots. But yeah, I mean that's true. That's true for any. Let me say it like this. That's true for any typical phase transition story. That unless it's the conformal phase transition that can be strong, most of the phase transitions usually are pretty weak. And this is, as I said, this logarithmic dependence on beta. If beta is very close to the horizon scale, that's great. But if beta is deep inside the horizon, that hurts us. And I'll describe this. Okay, but let me just say what I was saying to Michele, to everyone, so that we know this plot. This is the phase diagram of QCD-like theories, and here there's usually M up, M down, and this is M strange for the regular QCD, and it's mostly a crossover, but with two big islands of first order, one for very light masses and one for very heavy masses, and this is where the phase transition is first order. Okay, and in fact, this I think is even the simplest case. This is just pure gauge theory. So you add no quarks, pure gauge theory, that is going to be a first order phase transition. Okay, so that's almost the simplest thing you can have in a dark sector. Okay, so this is pure gauge. Okay, but of course, all the rest of the talk will not be about this specific scenario. You can imagine any kind of scenario you want, and these scenarios would have phase transition that run from very strong for for rare scenarios and much less strong for more typical scenarios. Okay, this is what, but I will explain exactly what strong means. Yes, sorry, there's a question. Sorry? Well, I mean, in this case, it's just the confining phase transition. Sorry? Yeah. Yes, they are in thermal equilibrium with themselves. Good, so we can talk about this. So the only thing we need is that there's a temperature there. You reheat this sector. Okay, so you reheat the sectors, but such that the temperature in the sector is less than the temperature of the standard model sector. Okay, so you assume that exactly. So N effective, as I said, it's the fact that this T is less than this T standard model. So you assume that the inflaton maybe decays to something, or maybe decays directly to these gluons, but less so that to the standard whatever the standard model reheating process. So that reheating leaves this sector with less abundance. Yeah. Any more questions? No. Okay. Good. All right. All right. And so let's talk about what this means. Okay. Okay, so what happens in first order phase transitions? Let me explain very qualitatively. Okay, so first order phase transition, we have if they're thermal phase transitions, they can also be not thermal. If the thermal phase transition, you're usually computing the free energy, okay, as a function of some order parameter, which can be like phi, some field in there, or it could be the gluon condensate in QCD-like theories, okay? And so what happens is that at high temperatures, at T much bigger than the critical temperature, it looks like this. At T equal to the critical temperature, you have another minimum, okay? And at T lower than the critical temperature, it goes here. Okay, so as the universe cools down, you go from this vacuum to this vacuum, but you cannot go directly because at the critical temperature, there's a barrier, and so you go over this barrier by tunneling. Okay, and the tunneling rate, okay, again depends on the theory, but the tunneling rate, the gamma over v, okay, goes like some prefactor that's usually very hard to calculate, and some exponential time-dependent rate. Okay, so this A usually is some bounce action. It could be S3 over T in case of thermal transition, S4 in case of non-thermal transitions, and it depends on temperature or the time in the universe. Okay, so this is going to be the important thing. This dependence will tell us how strong the phase transition is. Okay, and usually, okay, you can write AT. Okay, you can expand AT around some time, or the time of the phase transition, the time when the phase transition completes. In this way, has some A star minus beta T minus T star. Okay, this dependence where beta, okay, is just d log gamma by dt at some time, which is where the phase transition happens, which is just dA by dt, right? Okay, and this beta is the parameter that tells us how strong the phase transition is. Okay, so this beta is basically saying the following thing: you have a highly suppressed rate initially. Okay, it's at some early time at so high temperatures, this rate first is completely zero, then it's highly suppressed rate. But as you can see here, if you reach very low temperatures, the rate is nothing. There's no barrier anymore. Okay, and so this beta tells you how fast do you transition from this point to this point in time, okay, where the phase transition is exponentially suppressed so that no bubbles are produced, okay, and after a certain time, you produce infinite amount of bubbles, basically, or you roll everywhere. And so all the bubbles that you, all the interesting bubbles, right, which are the biggest bubbles. So let me say also like how this tunneling happens. So you have usually some critical radius of the bubble that you produce quantum mechanically, okay? But that critical radius depends on microscopic parameters, so it's microscopic. And then from there on, the bubble expands. And we will assume here that it expands with the speed of light, but that depends on plasma dynamics as well, and you can have terminal velocities as well. I'm not going to deal with this scenario, but this, of course, further would complicate things. But so you produce these bubbles at some very small critical radius that we will neglect, okay, and usually is neglected. But then they grow with the speed of light. But the time they have to grow with the speed of light is just basically 1 over beta. After 1/beta time, you produce everywhere so let me say it like this. This is the false vacuum here. This is the true vacuum. So this is the true vacuum. This is the false vacuum. Okay? And you have a bubble of the true vacuum outside of the false vacuum. But after a time of 1/beta, you everywhere the false vacuum transition to the true vacuum. So the biggest the bubbles can get is just basically 1/beta. Okay? So beta tells you how big are the bubbles. And of course, if you have a Hubble volume, then the Hubble volume cubed over beta cubed, or Hubble volume cubed over beta cubed is, or sorry, Hubble volume over beta cubed is going to be the number of the bubbles. Okay, so the bigger beta is, the smaller are the bubbles, and the more of them there are at collision. So this bubble will meet another bubble here. Okay, and this distance would be roughly 1/beta. Okay, so this is the things to remember. And this tells you that if you have a transition that very quickly transitions from a barrier to no barrier, that means that you have tons of bubbles, and probably this will be non-observable. So this is what Michele was saying about QCD-like transitions. They can have somewhat large betas, and so then you would have this transition being very quick, and the bubbles are small. But if you have small betas, sorry, just a second, then you have huge bubbles that can form the entirety of a Hubble volume, and then you have crazy large effects. Okay, so this is the thing to remember. Yes. Right. That's true. That's true. So it depends on now. It depends on the details, because it's true that if this is produced late, then you would be competing with the regular matter power spectrum at the same point where it was produced. Exactly. 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 Maybe if you do it before the CMB, as we discussed, but could be. But you're competing with the same. But so I mean, as long as at production the power spectrum is comparable to the matter power spectrum at those short scales, then yeah. So you can maybe think that there's a lot of energy density there, but and the inhomogeneity is 10 to the -2, but you're so deep that that at those scales the constraint is small. I don't know. So I mean, we have to think about this. But of course, you're right that there is a tail, and you have to be more careful. But mostly, this is what we are finding. Yeah. Right. Right. There could be, yeah, there could be. But yes, this is tail considerations. We are going to be talking about the peak. Yeah, sorry. That's true. I mean, it's not much lower, but it's lower. It can change some of the assumptions, but and can change some of the consequences, because if they're smaller, usually the collision is less violent, and so you produce less of a gravitational effect. So it can have an effect. We didn't study this, but it was studied in the case of gravitational waves, and there, yeah, for slower bubbles you get less gravitational waves, but there it's also important for other reasons, because baryogenesis depends on slow bubbles. So yeah, so then there could be other applications of this. But yeah, for now we just focus on light speed bubbles. Yeah. Yeah. Right. So you reheat this sector at very high temperature by the inflaton, but still much less than the standard model bath. Both of them redshift, and at some point this goes through a transition. Just so happens that it heats lambda QCD. Yes. Yeah. Well, for an SUN, yeah, exactly. For the non-perturbative case, no. Exactly. Maybe you could do it on lattice, but for something like electroweak phase transition, so perturbative phase transitions, it is computable. It's just a bounds dependence on temperature. Yeah, exactly. No, you cannot do it on Euclidean on lattices. Sorry? Yeah. Right, that's true. No. Yeah. No, we're not going to talk about models. From here on, it's just beta, gamma, and then you can extend our analysis if you want to slow bubbles, which we haven't. But yeah, I don't know what the effect will be, but could be. I mean, yeah, I don't know. Right. Yeah. Okay, good. Okay, let me continue. I don't want to run into lunch. Okay, so let me just say, so what do we do? Okay, so usually to calculate this, you would need to run simulations of the specific plasma, which is highly dependent on the details. But if anyone is interested in doing this, we're very happy to to collaborate and to get the results from that. I will explain also what do we actually need from the simulation. But let me just tell you what we do, which was actually also originally done for phase transitions, for calculations of gravitational waves from phase transitions, which is the most simple approximation. I say approximation, but it's not really a controlled approximation. It's, let's say, a toy model for a phase transition, which is called the envelope approximation. Envelope approximation. Okay, and this is due to Kosovsky and Turner from the 90s. So 93, I think. Yeah. Yes. Okay, and so this approximation is basically the following thing. You assume that the bubbles propagate with the speed of light, and that they're thin wall. Okay, so that is both of these assumptions. I mean, for some, the speed of light or not depends on the model. There are, of course, models that will give you speed of light propagation. Okay, and so here's the bubble, and here's another bubble, and at some point they will collide. Okay, and you assume that there's a thin wall. that's very well justified because the thickness of the wall is microscopic compared to the size of these bubbles, which is Hubble volume, comparable to Hubble volume. But then the interesting dynamics happen in the overlap region. That's where the interesting dynamics happen. And the envelope approximation just says you remove the overlap region. Okay, that's the most egregious part of this assumption, and that is that you just remove this, okay, and you just assume that there's no energy here. It's just true vacuum. Yes. Right. Good. So this. So good. So you have this kind of configuration. Okay, and this configuration tells you that there's a surface energy here. Okay, there's a surface here. So there's T mu nu here in the surface, and there's a volume difference. So here, this is just lambda. Okay, lambda difference. This one lambda, and then here, so this is lambda true, and this is lambda false. Okay, so as you can see, there's a T mu nu that you produce here. Okay, and from the Einstein equation, that means you produce the entire G mu nu. Okay, so both the scalar parts, so psi, phi, and tensor vector parts. Okay, so this is. So our lambda is the one inside. Okay, and I should say that all this assumption, the beta, we will assume that beta is large. This is what justifies the fact that these bubbles are still sub-horizon. We will neglect expansion on the timescales of the bubbles, and we would, in terms of cosmological production, we would assume that the bubbles collide instantaneously. Okay, and this will, I will show how this simplifies. Sorry? It's the wall, but it's also the volume. So there's both the surface and the volume. So there's both. Okay, and both are important. For gravitational waves, the volume is not important. For scalars, the volume is important. Yes, sorry. Yeah. Right. Sure. This is important. Good. So this is a reasonable approximation for vacuum bubbles, okay? Which is what happens not in the story that I say here, but what if you just have a scalar and that scalar has a phase transition, okay? That's the most simple thing where this would be the actual pretty good approximation. In the plasma, there's way more effects. It's much more complicated. There's turbulence effects, there's sound waves. All of these effects would further complicate things, but as I'm going to show, even this is already quite complicated. So we first want to just get the sense. And I think our next step would be to actually do just scalar transition. So just vacuum transitions, okay, exactly this way. And then the next step would be to do actual plasma calculations. And but as I think you can see, this has not been done at all. This is a fertile ground for a lot of actual very interesting cosmological signatures that can be very different in these different scenarios. So turbulence can be super important, very strong in plasma effects, and we completely neglect it here, but it actually dominates the gravitational wave production in some models. So it really is, I think, a fertile ground. So if you're interested in this, then please tell me, and I'd be happy to collaborate on actually calculating this. Yeah, of course. I mean, even just the simplest case where just a regular vacuum, the Coleman vacuum transition, is exactly this.
The guy that is standing is slightly larger than the constituent of the plasma.
Exactly. Exactly. I mean, if the masses of, for instance, if you take electroweak phase transition and the masses of the gauge bosons is small compared to the vacuum energy, this is what you get, because the friction comes from given particles mass, right? That's where all of this comes from. So yes. Good. So let me. You do. Yeah, you do. Well, in this case, it's also important. We calculate both of these effects. Yeah. So there is the effect. Yeah. You don't need a quadrupole. Yeah, absolutely. That's actually interesting. Yeah, but it's just that for all reasonable models, what happens is that, I mean, and the simplest calculation is where the bubbles collide quickly, and then roughly it's the same thing. The size of the bubble and size of the overlap region are comparable, so you don't get any parametric difference between these. But yeah, if you have like incomplete phase transitions or something like this, then you would have a contribution, unlike gravitational waves, right? So the reason we have only gravitational waves earlier is just that we also produce earlier scalar modes and vector modes and everything, but gravitational waves propagate while the rest of the metric does not. And so everything else gets washed out except for gravitational waves. Whereas here, you immediately see these effects, okay? But let me get to the effects so that I'm a bit running out of time. So let me continue, okay? And so then we basically calculate this probabilistically. We just take points, like we take a 2-point function and we ask, what if these 2 points are inside the bubble? What is the chance that they're inside the bubble? What is the chance that they're on a surface? Okay, I say this in few words, but this has been a year of calculation by Salvatore that is, we're still checking the results. So even this envelope approximation is quite hard. This probabilistically, there's tons of integrals to calculate, and we still are not sure that they are correctly done. That's why the paper is not out yet. But at least conceptually, this is what has been done. Okay, so it's the question of if you want to calculate a 2-point function of the T mu nu, which is then propagates into the Einstein equations, and this 2-point function depends on whether it's on the surface, if 2 points are on the surface of the same bubble, if they're on the surface of 2 different bubbles, if one is on the surface and the other is on the volume, or if both of them are in the volume. Okay, so this is the crux of our calculation, but I'm not going to go into it because the details are hard actually. Okay, so this is what is being done, and then this feeds into the Einstein equations. Okay, so let me do it here. Okay, so here let me talk about the Einstein equations. And well, more broadly, the Boltzmann equation, also for dark matter. Okay, so this would be here. We would assume basically the following thing, that this is Einstein equation plus the equation, the Boltzmann equations for dark matter. Because as we will see, this perturbation exists a very short amount of time. It produces a, if you want, a delta function in the gravitational potentials, and this in effect causes a matter perturbation that then keeps those effects in memory. Okay, so this is what is being done here. Okay, and we do the usual thing. We can calculate so we can take the T mu nu. So the T mu nu would be the T mu nu of this dark sector, okay, and the T mu nu of regular dark matter. Okay, so matter. Okay. And in matter domination, okay, we can put the equations in this form. Okay, so we get an equation. Okay, so let me get them at least once. I will write them. Sorry, minus 3 over eta squared zeta that I can never write properly. So excuse me for my very horrible zeta. And then some source that I will explain what it is. Okay, and equation for z. No, this is not zeta. I hate zetas. Okay. Okay, and these S1 and S2s are the following thing. Okay, let me write them here. Okay, I will write them here. So S1 is 2 pi g Newton a squared over 3 rho dark sector minus 6h squared over k squared and dark sector. And now this is not visible, sorry, let me write it, because I do want this to be seen. Let me write it here. Okay, so S1 is this, so 2 pi g Newton a squared over 3 rho of dark sector minus 6 h squared over k squared n of dark sector, and S2 is 8 pi g Newton a squared over 3 n dark sector. Okay, so this is a long way of saying the following thing. So zeta is the regular gauge invariant dark matter perturbation. Okay, so zeta is 1/3 delta matter plus psi. Sorry for these notations. They are Rubakov notations, so if they are confusing you, there's minus signs in certain places that are annoying. And so these S1 and S2 are our sources due to the bubbles. Okay, so rho is the rho of the bubbles, and n is the anisotropic stress of the bubbles. Okay, and so one of the problems that we have is that both of these are k independent. That's what we find in the power spectra. The dimensionful power spectra are independent of k in the low k limit. And so here there's a very weird IR divergence that we don't yet understand. It doesn't affect any of the results, but we're still trying to understand what it is. So if you have an... Sorry, which one? This one? Exactly, yeah. So this is the regular... Yeah, you do. So you have them separately. You see, you have two equations. So it's just that it's convenient to put them in this way. And if you want, this combination is the actual matter combination that you produce without the curvature. Okay, so this is the thing that reacts slowly to the sources, and the other one reacts immediately because it's the curvature due to the sources. Okay, so that separates it. If you want, if you go, for instance, to the how's it called, spatially flat gauge, this is literally the matter perturbation in the spatially flat gauge. Okay, so that's convenient. Okay, so we still don't understand this. So if anyone has an idea on why, yes. Right, exactly. So for neutrinos, for instance, this goes like k squared, and this. Sorry. Yeah. Yeah, and everything's finite, yeah. So here it's just the fact that you have these bubbles, right? So you have anisotropic bubbles in each horizon, gives you some anisotropic stress that at large scales, the anisotropic stress just behaves like white noise. And this is the only thing that's giving those results. But also, let me just say before, so these are the things, so these S1 and S2, we will assume are simply delta functions, okay? They exist for a short time because this is just the bubbles and they're gone. In principle, of course, the bubbles collide and produce radiation, and that keeps these effect longer. But for simplicity, this is what we assume. Maybe that's part of the problem in the calculation. But I should also say this affects nothing. So none of the observables actually depend on this. And so I think the results still hold, and they make perfect sense in terms of the parametrics. And they also align with the parametrics that the Yushin group has been getting. So we think everything is probably fine. But still, if you have an idea on why these effects are there, we're we're very happy to hear. But also these S1 and S2 are the first step of what we would like to get from a full simulation. This is basically I mean, these effect as a function of time, or if you want the prefactor of the delta function in the limit that the phase transition is very fast, is what we need to get. So this is the information from the phase transition, and then this feeds into evolution of the psi and the zeta. Okay? Yeah. It's a white noise, yes. With random if you want random tensor directions, yes. 1/k² for some reason. Yeah, so this is what we don't understand. Right, it is constant. So the n-dimensional full power spectrum is constant. But then what happens if you look at the Newtonian gauge, for instance, Newtonian gauge equation, the traceless IJ equation gives you that, you know, the potentials, the psi and phi, scale like 1/k² n. Okay, this is the problem. So then this is just, it's just Laplace equation or Poisson equation for the gravitational potential that depends on this directly. So we don't understand if this is a gauge artifact. And also I should say we calculate all of these effects neglecting expansion. So it could be that somehow when expansion is taken into account in the S1, S2, that also takes care of it. And I should say the following thing, that it only causes problem in superhorizon. So if you're deep inside the horizon, both the IR and the UV tail, everything looks normal, everything is white noise spectrum. Only somehow, as you can see, when this K is smaller than horizon, suddenly you get this crazy, weird 1/k². Sorry? Yeah. So, but in fact, all of this is deep within the horizon. It's only integrating over scales. So these bubbles are small, but somehow integrating over scales larger than the horizon gives you a weird result. So maybe you need to consider expansion because you can have corrections of that order. It's plausible, but we don't immediately see how this would correct it. So yes, it could be.
One of the issues that this approximation that you can do in the sky, the bubbles are colliding in Minkowski.
Right.
So now if I take 2 points that are very far away from each other, we aren't sure.
But it's not actually coming, so we see it. It's not coming from the 2 points being far away in the integral. So it's coming from the 2 points being actually close. All the integrals are dominated by 2 points being on one bubble or on 2 bubbles very close to each other. And for some reason, it could be that there's a bug in the code. It could be that there's the expansion, or it could be that we are incorrectly assuming when we're going from Minkowski to the actual FRW, we could be doing some weird gauge choice that fixes, I don't know. So we have been exploring all these possibilities. We haven't found anything wrong so far. But also, as I would say, let me just say one more thing. If we take everything in Minkowski, everything is completely well behaved. It's somehow the super horizon limit that is weird. Yes, sorry. These, right? So they. Yeah, exactly. That's it. that is the whole point. That is the constraint. Yes. So this will generate exactly ISW and matter power spectrum effects. Okay. So this is what we will get. Okay. So let me exactly explain this part, which is the last part. Okay. I can do it here. Good. So the last part is constraints. Okay, and predictions and projections. Let's say it like this. Okay, and we are here considering two effects. One is ISW. Okay, and so to the cosmologists in the room, usually ISW is something very small that you can usually not care about at all. But this is because of a coincidence, right? So ISW is just the following fact that when you look at the delta T over T of the CMB, right, you have Sachs-Wolf, you have Doppler, and you have this ISW effect, which is just this thing, okay, from recombination to today. And this is the ISW effect. But then there's the very weird coincidence of matter domination that this just vanishes in matter domination. So that's why we have late ISW, early ISW. This comes from the fact that these don't vanish late and early. But if you suddenly have a perturbation that produces almost step function in psi and phi, this produces a huge ISW effect. And so this would, in fact, be a very significant constraint. Okay? And if you're not a cosmologist and you're interested in what is this effect, it's basically the fact that these bubbles produce gravitational potentials. And these gravitational potentials, they change with time. So the CMB light goes through the bubbles with gaining a redshift once they enter, but once they exit, they get a different redshift. And so the light that went through these bubbles, because this potential difference is inhomogeneous, that even though the light that got in was homogeneous, created an inhomogeneity or anisotropy in the light. Okay, and so this is what you're basically sensitive to. Okay, this is one effect. Okay, and the other effect is just the LSS, so matter power spectrum. Power spectrum. Okay, and this is just the following effect that that you would get that you basically produce psi and delta matter, okay, after the phase transition. Or if you want, you have a brief period where you had a gravitational well. You have some matter that is falling into this gravitational well, and this created a new structure. And that structure after that then grew, depending on how much time it had, because this is all inside horizon stuff. And then if that structure is bigger than the structures that we see, of course, that is constrained. Okay, so this is basically the two constraints that we are considering. Okay, and so for the last part, let me just show you this constraint that we have, okay, and show you the result of our calculations. So hopefully this works. Okay, and so these are, first of all, let me just go on and show you the sources. So this is S1 and S2, but they're power spectra. And you can see this weird behavior, especially for beta over H. So beta H is basically the size of the bubble compared to, or sorry, horizon over size of a bubble. So this is where the bubble is 100 times less than the horizon. This is more typical for phase transitions. 10 is for very strong phase transitions. So you can see this behavior that all of them do scale. This is the dimension full power spectrum, so it scales constant in this range, right? So this one is basically k of order beta, okay? And so this you can see k over beta, and you can see or the k over a beta if you're looking at the co-moving one, and you can see this typical behavior. But then in super horizon, for some reason, there's this divergence that we don't understand. Okay, and of course similar for beta equals 10, but just less region between the horizon and beta. Okay, so this is these power spectra. They both are the same order, and there's also the cross correlation. It's 1 over k to the 4. Sorry? Sorry, this? That's the cross correlation of the two sources, these two sources. Of course, it's the same bubble, so they are all correlated. Okay, so it's just a source for, there's two basically sources. I think it's some adiabatic and isocurvature perturbation, but we haven't figured out exactly how these are separated. but they are correlated. Okay, good. And so then this is the ISW that you would, this is the CMB that you would produce through the ISW effect. ZPT is basically the redshift at the phase transition, okay, and this is for beta equals 100, and omega of 10 minus 2. You can see this is on the verge of being observable because it's just 1 order of magnitude less than the regular CMB, okay, so this would already start feeding into the errors, and so this is roughly, sorry? No, it's very small, but you compare to the entire spectrum, right? So this is the CMB, the CMB anisotropy that's created by the phase transition, that is created by the ISW effect, compared with the total CMB regular lambda CDM anisotropy. But regular is very small. It's well, it also in different L's, right? It's mostly here and in very high L's. Sorry, no, it's larger on this scale. Yeah, I don't. No, I think it's large. I think it's here. It's about. Yeah, I think it's here. It's somewhere here, but then here it's very small. But it doesn't matter, right? Because we're comparing. Yeah, yeah. It's large, but it doesn't matter. We're. Right. Yeah, I think around it's around the entirety. It's around order 1. Significant. Order one of the Sachs-Wolf. Yeah, but it doesn't matter, right? Because we are comparing. This is I mean, the right comparison is the CMB that we produce compared to the CMB or the anisotropy that we produce compared to the full anisotropy. Yeah. So and of course the reason why we do produce ISW in this range, which is significant, is because we get very significant phi dot. Because I mean, of course, after the phase transition finishes, phi dot goes to 0. But then at the production, it is large. 1/2? Yeah, good. This thing, yeah, of course. Exactly, yeah, exactly. This is, and you can see, this is very typical parameters. So this is fully, let's say, it's not a strong phase transition. This is more like a regular phase transition, slightly on the stronger side. If you take beta to 10, this shuts up by a lot. So this is I think that's correct, right? So Salvatore. So the constraint, I mean, if you just look at the peak and compare this to like percent level of the, it's roughly similar, yeah. Yeah, exactly. Right. So this would be constraint, yeah. This would be constraint, yes. Yeah, I'll show you constraint in a second, okay? So, yeah, sorry, there was a question? So there's no Sachs-Wolf and Doppler because at the time of a combination, there's no phase transition, there's nothing. Sorry? Yeah, good. So this is exactly, that's the closest limit. So there you would, if you really need to, if you want to, and this is here just to show like the limiting case. So this would be where you would need to start to include also recombination effects. Good. So yeah, so Sachs-Wolf Doppler. Good. So and then this is the matter power spectrum that we produce. It's slightly weirder because it also grows depending on beta, but again, it's comparable to the matter power spectrum of lambda CDM for the same parameters. Okay, and then we can show the constraints and the projections. Okay, so ISW is the constraint. You can see that the constraint is on omega pt over 10 to the minus 5. So omega pt is the row in the dark sector compared to the row in the visible sector at that time at the time of the phase transition. So this is not today. This is not comparable to today, but this is comparable to to the time of the phase transition. That's why we call this omega pt. Okay, so this is if omega pt is 10 to minus 5. That means that the dark sector is 10 to minus 5 of the total energy density of the universe at the time of the phase transition. And then it goes like, there's a factor here of 10 over beta h to the 5/2. This is also the scaling that Yushin has got in his recent paper, from today also and from previous papers. And so you can see that the ISW effect, if beta is 10, the ISW constrains omega pt of order 10 to the minus 5. So for very strong phase transition, you can constrain a dark sector which is inhomogeneous at 10 to the minus 5 level of the background. Whereas, of course, if beta is larger, so weaker phase transition, this scales away, but still within the range where there's no also ineffective constraints. Okay, so this is the ISW effects, and then from the matter power spectrum, these are projections from Euclid, I think. Yeah, perfect. And this is similar constraints, and they would get even stronger for very weak phase transition. Okay, because then you probe. In this case, what large-scale structure gives you is that, of course, you get weaker phase transition, but also you shift the peak towards the smaller scales where you have more constraining power. Okay, so these two effects well combine to give you stronger effects. And so this is it. Again, there's a lot of more stuff to do. This is really the basic stuff. So if you're interested, talk to us. I think there's full range of possibilities here that has been completely unexplored. So thank you. Sorry? I mean, it's not the ISW curve, it's the constraint. Right. No, I don't know. Maybe. Why does it change? Why does slope changes slightly around 100 and around 5? I mean, this is all order 1 effect, so it's not. I don't think we thought about this. Yeah. Why? I mean, here I think it's the dark low L, probably low L. Yeah, right. Yeah, that makes sense. That's true. Yeah. So it's good. But it's really, you can see that it's really order 1. It's not a parametric difference. Yeah. Yeah. How? Sorry, the what? NS. Well, yeah. I mean, I mean, of course, it completely tilts it if you want. But this, I mean, we just naively excluded this from the error bars. We didn't do the full Bayesian reanalysis with this. But yeah, you can. I mean, I guess if you put this in, you can get a different fit for NS. I mean, but if you put this into the whole Bayesian fit, and suddenly you have. Yeah, it is. Yeah. If that's the question, yes, then it is a very bumped structure. You would, I mean, the tail of the bump is like k cubed on the dimensionless power spectrum. So I think this is. Yeah, it's not a flat power spectrum, right? It's not. I mean, it's a subhorizon. It's a subhorizon like physics with a typical scale. So you would not get like inflationary perturbations. You don't produce stuff in outside the horizon. Sorry, yeah, more questions? Lunch. Thank you.